Hey everyone, we are continuing on with exponentials today, and we're going to talk about simple, compound, and continuous interest in regards to banking. And to start us off, I actually wanted to kind of warm up and or practice with expanding logarithms, which is something that we had done in 3.4. So if you're confused, you can kind of go and take a look at those notes. As well as simplifying logarithms, so having multiple logarithms and then combining into one. So this should be in your notes, kind of the first thing that we're going to tackle today. And I can potentially probably put up some completed answers for these. Otherwise, it should kind of be relatively straightforward. So see how it goes, just to kind of get back into the swing of things as our warm-up. The lesson today is going to revolve around banking and how often you're rewarded for having money in your bank account. So in our first situation here, we have a bank account that offers 12% yearly interest, and this is going to be compounded, once throughout that year. So it's only going to be calculated once. So suppose that we had deposited $100, how much would be in the account after 1 year? So my savings over time equation here would be 100 times 1.12 raised to the first power, because I'm only going to be getting that money once. Okay, so then if I'm trying to figure out, okay, well, after 1 year, how long is this going to happen? Actually this first equation, so if I put a t there, this s of 1 would be 100 times 1.12 raised to the first power, which we don't really need a calculator for. We're just going to end up getting $112 after 1 year. A different option that the bank has available to you is, instead of giving you that 12% at the end of the year, they can say, well, let's give you a piece of it over the course of the first 6 months, and then the other piece during the second 6 months. So how is this going to kind of change our equation is, I'm still starting with the same amount, but the interest that I'm going to be awarded here is 1.06. And then for my equation, what I actually want is 2t. And that's because I'm going to be, if this is every 6 months, then I'm going to be awarded that twice within a year. So I want to be able to plug 1 into my equation. I want to be able to plug in basically the number of years into my equation, and I want it to multiply by 1.06 actually twice, okay? Because it's going to do it in theory like around June, and then it's going to do it again in December. So in this case, if I take a look at what's going to happen to kind of my end result, so this becomes 2 times 1, or just squared. I can make a guess as to what's going to happen to this total amount of money, but after I plug it into the calculator, I end up getting $112.36. Okay? So we end up making more money than we had if this was only compounded once, right? It's not much of a difference, but between $112 and $112.36, we obviously have more money if we're compounding every 6 months. So if we're compounding quarterly, how would that change our equation? Again, they're not going to give us 12% 4 times a year. This is going to be, I'm going to take that 12% and divide it by 4, and then here I'm going to put 4t in my exponent, because they're going to be paying out 4 times a year. So let's see, if I plug 1 year into this equation, notice this exponent is going to eventually become 4 because I'm multiplying by 1.034 times. So I'll go up, we'll switch this, and now I'm going to be making $112.55. So even more, so on and so forth. Here I'm going to do monthly. If you want, you can try and practice and see what that would be first. Otherwise, I can kind of show it to you here. So after 1 year of doing this, I would end up with, let's see, 1.01 raised to the 12th, $112.68. So obviously it's not a huge deal, but the difference here is going to be basically that, in any of these situations, after that first, rewarding of my compound interest, I'm then going to be gaining compound interest on already the additional money that I have. So we want things to be compounded more often because that means that the increase in our money is also contributing to the amount of money that I'm going to be making. All right, so which option provide the best? So more frequent. And it's because we are gaining interest on our interest. Right, so interest is the amount of money that we're gaining just for having our money in that account. So as that goes up, I want that to also be contributing to the amount of interest that I'm getting. So here we end up with our compound interest formula. So if something is being compounded a certain amount of times per year, then this is the equation that we're going to use. And really it's no different from, this is, let me get rid of that. We started with this as our exponential equation, and this isn't too far off from that. Our starting value is A, so often known as our principal. So this is our starting value. Our interest rate here. So we can see kind of in this part there, what we're really doing is taking that interest rate, dividing it by how often this is being compounded, and then adding it to 1. So this is what's turning it into a percentage. So this little piece here is why we ended up with 1.06 or 1.03, 1.01, is because we were taking that rate, dividing it by a half or a fourth or 12, and then adding it to 1 to kind of get it turned into a percentage there. And then finally, our exponent, normally we would just kind of see a t there, but because we're changing that compound period, we're going to be changing this n value as well, or we're at least going to have that as part of our exponent, is how often we're doing this per year. Okay, so that's what our compounding period is. So this is basically how many times per year. So we've said that if I do this more often, it's beneficial. Well, in the case where the bank is continuously giving you money, so it's almost like every millisecond that they're going to be kind of rewarding you some money for this, then we end up having this equation here, which is continuously compounding interest formula. And the only component to this that we potentially don't have our full grasp on is this E value. Again, we talked about it yesterday as being 2.718, but I'd also encourage you to find that button on your calculator because it's going to be kind of used more and more as we go through here. So here, if I just kind of label what my variables are, they've given me a P saying, hey, this is the amount that I'm investing. They've given me R, which was my interest rate, and they've given me a T in this case. So if I were to come up with and try to match the variables to this, 100e to the 0.12, and then just because we're already doing a specific example of time being 1 year, so I'm going to plug in that time. And let's see what we get if I was doing this continuously. So if I was basically always receiving this interest over and over again, and this ends up being basically the maximum that I could ever get at this 12% interest rate, I basically end up with, and I'll do it just around here, $112.75. So I can't compound any more often than that. So that is basically my upper limit here. And if you want, and you can't find this E button on your calculator, if you want to call it 2.718 while you're remote until we can find the actual value, just let me know. Otherwise, let's do 2 example problems and we'll kind of see using this equation or this equation what we can come up with here. So Brenda invests $48.48 in a savings account with a fixed annual interest rate of 5% and is compounded 2 times per year. So it's not compounded continuously. So the equation that I'm going to go with is that P of t principal 1 plus r over n to the nt equation. And then I'm going to write the specific one for this problem. So my initial amount invested was $4,848. This is going to become 1 plus 0.05 divided by 2 because it's 2 times per year. And I'm just going to leave this as 2t up top. And I'm probably showing you more than what you need, but I'm trying to kind of clearly go through what this expression is really doing. So this would then simplify all the way down to 1.025 raised to the 2t. Okay, so if I take that 5%, I'm doing it twice per year, that's really 2.5% or 0.025. The 2 times per year is also in my exponent with that 2t. And now they're asking, well, okay, what is it going to be after 6 years? So now I'm going to plug this in. So 2 times 6, or 12, is going to be my exponent when I go to type this in. So I'm saying 4,848 times 1.025 raised to the 12th power on my calculator. And I'm getting an answer of 6,520. Because we're talking about money, I can safely leave it at those 2 decimals, okay? So here we've got 2 cases, so this is going to be another one in which we're compounding 2 times per year, so see if you can model it off my work. And then here we've got something compounded continuously. So for that equation, we ended up with this is kind of what they have for our model. I might just change that left side to like P of t or S of t just for savings over time. So here, my savings over time is going to be equal to my principal, which is the initial amount invested, times E raised to the, so I have 9% times time, so that's 0.09 t. So that is my equation. If I'm compounding continuously, all I need to know is the years, which they've provided for me. So now I'm figuring out S of 15, 2,658, E to the 0.09 times 15. And I'm going to plug that into my calculator. Again, treat E like 2.718 if you don't know where that button is on your calculator. It's hard to kind of explain it to you verbally because we've all got different stuff. But our savings after 15 years in this case is $10,253.04. All right, so there's not too many kind of additional practice problems here. I just wanted us to make sure that we've seen this application. So you're going to do one more compound, looks like another continuous, and then between these just kind of decide which equation that you need to use and calculate that final value. All right.